Welcome to the lecture on TTT diagrams, that is also known as time temperature transformation diagrams. So, we studied a bit about the phase transformation, and we knew that phase transformation is normally what we have studied is that it is by the mechanism of nucleation and growth, and then based on that you can also have the expression for the transformation rate, which is basically a function of nucleation and growth. So, you will have based on that expression further you can have you can get the concept of the transformation of one phase to other with respect to time. So, with time how the transformation will will be there. So, basically we are interested normally when we in industrial practice or in normal case also we are interested to know that when we are changing the temperature. So, what way other phase will be transformed, how it will transform, at what time, how much amount will be transformed. So, for that basically there are two kinds of diagrams. One is time temperature transformation diagrams, and then further we will also discuss in our next lecture about the continuous cooling transformation diagrams. So, they are normally known as TTT diagrams and CCT diagrams. So, in this lecture we are going to have the discussion about the time temperature transformation diagrams. So, what are these time temperature transformation diagrams? So, we discussed about the phase diagrams, and we knew that they are basically also known as the equilibrium diagrams. So, in that whatever phase we see which is formed, basically that is formed at an extremely slow cooling rate, and they are not very much feasible cases, because in industrial practice that cooling rates are these cooling rates which are there, they are not so slow. So, we can have the cooling rate, we can choose it deliberately very at any value, and obtain the desired transformation product in steel. So, for understanding the effect of cooling rate, transformation is to be followed both as a function of time and temperature. So, what we need to understand that when we are cooling, then there are two things. One is time. So, with time how this transformation is being carried away, transformation proceeds, as well as at what temperature. So, basically when we are we are talking about transformation at any point. So, we are coming to one temperature, and at that temperature with time what will be the transformation. So, how the phase will be transformed. So, that is basically for that we will in this lecture we are going to discuss about the TTT diagram. So, TTT diagram that will be depicting the relationship between time, temperature and transformation. So, in this case as you know we will be discussing about the time. So, you will have on x axis you have time, and on the y axis you have temperature, and then you will have so we will discuss that how we can see that how the transformation proceeds. So, how can we understand about it? Now, what we do in this case, we are basically heating the steel specimen to austenitic range, and then we are quenching into molten bath that is maintained at different temperatures in the perlitic region. So, basically we are talking about any composition. Suppose you take the eutectic composition. So, in this case what we see in the case of eutectic composition, that is about 0.8% carbon. So, the austenite will be converting to perlite, that is ferrite plus martensite. So, there will be perlite transformation. Now, so what we do is that first of all you have to go into the austenitic zone. So, as you know that you have such is the iron carbon diagram. So, this is your eutectic composition, this is about 0.8% carbon. So, this is your temperature, and now this will be further. So, this zone is the austenitic zone. So, when the so if you talk about this composition, so when the temperature will come at this point, then it will be converting to martensite, I mean perlite in normal cases. So, this is what you getting, this is the composition, that is so here you have in this side ferrite and this side you have cementite. So, mixture of ferrite and cementite in alternate lamellae. So, that is known as perlite. So, ferrite, so austenite will be changing to perlite. Now, what we do is that you are heating that specimen in the austenitic range, you are going above 723 degrees centigrade. So, you are going somewhat above, so that whole specimen is austenitized, whole of the specimen is austenite. And then we are quenching into molten bath maintained at different temperatures. So, what we will do, you maintain the molten bath at different temperatures below that lower critical. So, that is something close to 730 degrees centigrade. So, basically you have you heat in this zone, and then you maintain it a molten bath of temperature below this. So, you take a particular temperature, and at this temperature the molten bath is maintained. So, that molten bath has this temperature maintained below this temperature. So, that this temperature will be taken different in different set of experiments. So, in that bath you are going to quench the molten this specimen which is there in the austenitic range, and since this is a perlitic range, so we are writing the perlitic range. Now, since you are going to a temperature, you are putting the specimen into the molten bath which is maintained at temperature below this lower critical temperature, which is the transformation temperature. So, certainly there will be transformation started. Now, what happens that this specimen will be allowed to transform partially to perlite by holding for a certain length of time in the bath maintained at a particular temperature, after which it will be quenched to room temperature. So, what you do is once you are putting that in the molten bath which is maintained at some temperature below that temperature, below that lower critical temperature, then you keep it for some time, and then so expecting that there will be transformation to perlite, and then you quench it to room temperature. So, that way you will have the austenite which is untransformed. Suppose there will be some transformation after certain time of austenite to perlite, but then after that since you are not holding for infinite time, so after some time you are going to quench it into room temperature, quench it to a bath of which is maintained at room temperature. So, whatever austenite is there, if they are quenched at room temperature, so fast cooling, in that case austenite will convert to martensite. So, all the untransformed austenite will be converted to martensite on quenching. So, some part, if it has transformed, it will be transforming to perlite. Otherwise, the rest austenite which is not converted so far, so that will be converted to martensite. So, at any particular temperature of holding, and if you are allowing for different holding time. So, with different time you will come to know that what is the amount of martensite. So, that basically will tell you that that much was austenite which has been transformed to martensite, and if there is transformation to perlite, so you will have perlite, and then martensite. So, if there is no transformation, it will be only martensite. If there is suppose 2% of perlite and 98% of martensite, it means there is 2% of transformation. So, this way you can have you can see at any particular temperature, you can see that at what time the transformation has started. So, that will be 1% line, and then at what time the transformation has completed. So, you normally give 1% as well as 99% perlitic transformation. So, that that is basically noted, and then this will be done at all the different temperatures, and accordingly you will have a series of points, and then you join these lines. So, similar tests are conducted at other temperatures in perlitic and bainitic region to determine the full C curve for the start and finish of the transformation. Now, these austenitized specimen, so they will be quenching to different temperatures in the martensitic zone. So, that will be different. So, what we will see now, this is how it looks like. So, what you can see that you will have this is the TTT curve for the eutectoid steel. Now, look at it. So, this is your 725 degrees centigrade, this is your equilibrium temperature. Now, from here you are basically cooling the. So, suppose you are holding the bath at some point here. So, if you hold this bath maintain at suppose 720 degrees centigrade, and if you suppose and this is a time. So, this is in logarithmic scale. So, this is 10 to the power 2. So, you can see that at this temperature somewhere just above 700 or 710, you are going till this time. If you are up to this time, even if you are coming and you are further quenching into the quenching at room temperature, then you are to get 100% of martensite, because there is no transformation up to this point. Now, when you are at this temperature, suppose 710 degrees centigrade, you are coming to this time. So, if you are having this time, so at this point you will see that this transformation was there. So, this line is shown as 1% and this is known as 99% transformation lines. So, at this point it will start as 1%. So, it means 1% means there will be 99% martensite, and here it will be 99% suppose. So, it is you see that it is taking large amount of time. So, certainly when there is very less undercooling, then for the transformation to proceed to get the perlitic structure, you will have to wait for so long. So, transformation takes a lot of time. So, at this temperature you will have this point as well as the different points you will get, and you will get the 99% point line also. So, this way at every temperature you will have 2 points you will be getting. Now, you come to different temperature, then at this temperature you are going to get this line, this line. So, that way as you come down to initial quenching. So, as you know that you are austenitizing first into the temperature which is above this temperature, and then you are first quenching in a bath maintained at some temperature. So, if you come to this temperature, which is a minimum time at which the transformation will start and it will end also at minimum time. So, that is known as the nose of this curve. And then as you go down, so that curve looks like this. So, these curves which you are getting, that is known as the TTT curve. Now, in this, because this is also known as the isothermal transformation curves, because you are talking about the transformation in an isothermal manner. So, the transformation is occurring at a particular temperature, and that way you are getting those locus of these points, and accordingly you are drawing these curves. Now, these curves will tell you that in what case the perlite will be formed, where the fine perlite will be formed, where the coarse perlite will be formed, which one is the benetic region. So, in this case you will understand that when you are basically putting the material standardized specimen into a bath which is maintained at different temperatures, what kind of basically the microstructure you can think of. So, if you are doing this temperature, you are putting here and you are holding, and so what you see that in this zone you are getting the coarse perlitic structure, and this is the zone which is for the fine perlitic structure. Similarly, if you are going to this zone, so that zone basically will be the benetic region. Now, what happens for benetic region? What you have to do is, if you are coming directly, you have this temperature bath, you come to this and then you hold it for in this bath for some time. So, at this because it is not it is the past the nose of the C curve. So, it is coming here, and then if you are holding it, so you can have these benetic structure formed. So, you will have coarse benite as well as the fine benite structure in these cases. So, basically what you see is that you are going to have these two lines. Now, what if you are cooling from here directly to this temperature? So, you are going to get directly the martensite. So, basically that is basically the critical cooling rate. So, after if you go past below this C curve, so this cooling rate will talk about the critical cooling rate where you are going to get 100% martensite in such cases. So, so that way this is the significance of this TTT curve. Now, further if you look at this curve, so what you see in this case, what you do is you are coming, you are going into the different temperatures, and then you are coming to different temperature here, suppose below, just below MS. You are coming to this temperature, and then you are so your transform, there will be some fraction of martensite formed, and then you are further heating and then cooling to room temperature. So, now what happens in that case, the martensite which is formed, and then if you are further heating, then that will be tempered martensite. So, you will have two kind of martensite, tempered martensite as well as the untempered martensite. And because of the change in the color, because of etching, you can differentiate between the tempered as well as the untempered martensite. So, if you select the different temperatures and then you do this process repeatedly, so you will have an idea about the martensitic start as well as the martensitic finish temperatures that you can get. So, this curve shows. So, this curve this is the one here, you are holding here itself, and then you are going just below that also. So, like that if you do, so you will have the line for MS and MF also determined. So, that is what it is. Or standardized specimen, they will be quenched to different temperatures in the martensitic range, and then they will be further heated to temper the martensite formed, and then further they are cooled back to room temperature. Now, these tempered martensite, so they can be differentiated from untempered martensite under microscope. So, you can have the idea about the fraction of martensite corresponding to the first quenching temperature, so that can be determined. Now, also amount of martensite formed at different temperatures as well as MS and MF temperatures, they can also be determined using this curves. So, what you see is that when you are coming to, so this zone is the gamma zone, this is the perlite zone, and this zone, in this zone you will have gamma plus perlite in this upper portion and gamma plus benite in this upper zone. So, if you are coming to any temperature here and then you are quenching. So, in that case the gamma will be changing to martensite, and the rest transformed product will be as it is. So, if you are coming to in this zone, you will have some gamma which is transformed to martensite, and then rest will be perlite. So, and if you are crossing this line, in that case all the gamma is transformed only to perlite. So, there is no point, there is no chance of having any martensitic structure. So, that is about that is about how it is, there is transformation from austenite to perlite or benite or so. Now, what we mean to know further, that you may have the steel composition other than eutectic also, and if you have composition of either hypoeutectic or hypereutectic, in that case the phase transformation mechanism will be different, and the TTT curves will also be looking somewhat different. So, that can be understood by looking at the what will be the change in the TTT curve. So, when you have hypoeutectoid steel, so that is say less than 0.8% of carbon. So, if suppose you are taking say 0.35% carbon, so for that carbon steel. Now, in that case what happens that if suppose this is the time of 1 second. Now, in that case what happens that for the hypoeutectoid steel in this range. Now, in this range what will happen that transformation will be starting from here, and say suppose this is your 0.35%. Now, in this case the transformation will start from here, and this zone is basically alpha plus gamma. So, you will have a zone of alpha plus gamma. So, what happens, you will have this, suppose you will have another temperature, so which will be above that 725 degrees centigrade, and you will have this as the 725 degrees centigrade, and this is somewhere close to 800 or so. Now, in this case what happens that so it will start from 1 second, and this will be 1 minute, and this will be 1 hour or so. So, the line goes like here. So, what is there? So, your above this temperature you have gamma, and this zone is basically alpha plus gamma. Now, what happens that your transformation line moves like this, and it will be coming. So, ultimately you have this transformation which is about what we have line which we have seen earlier, that is this line, and this region. So, it will starting line will be this, and you have finishing from here. So, this way the lines will move. Now, this will be your alpha plus perlite, because you will have the proeutectoid ferrite formation. So, you will have proeutectoid ferrite plus perlite. Similarly, you will have alpha plus gamma plus perlite in this case. So, what you see that in this case, this is 1 second. If you look at this point, now in this case if you see, so this is here, this is somewhere close to 1 second or even more, this nose point is for the eutectoid steel. Now, in this case what you see that this is less than that, it is about 0.2 seconds. So, it is towards that. Now, in this case getting a complete martensitic structure will be very difficult. You will have to have very high cooling rate to have the fully martensitic structure. So, that is the main difference, and also you must be knowing that when you are coming from that temperature, in that in that case you will have the alpha plus gamma zone, and then once you go below that temperature further, then alpha is already there and gamma will be again changing to gamma plus. So, that will be going towards the perlitic transformation. So, that way your transformation will proceed. Similarly, if you go for the hypereutractoid steel. So, hypereutractoid steel will be towards this line, and in this line rather than alpha you will have the cementite on this side. So, if you try to draw the TTT diagram for the hypereutractoid steels. Now, in this case what happens if you take this as the 1 second line. So, you will have again a line, and in this case so this is your A1 line, and you will have so ACM line. Now, in this case what happens that you will have this cementite plus gamma. So, that will be coming. So, you will have this will be your cement gamma plus Fe3C, and then this line will come, and then it will go like this. Similarly, so this line will be from here it will be moving like this, and there will be so this will be start, it will be starting, and then it will be finishing will be like this. So, basically at this temperature if you go like this will be the transformation start finish. So, you will have in this zone you will have Fe3C plus perlite, and this will be gamma plus Fe3C. So, here again you see that this is close to 1 second, whereas this is quite early. So, in this case this hardenability basically can be seen that hardenability is less. Your chances of conversion to martensite becomes less, because you will have to apply very high cooling rate, then only your these lines. So, it will be you will be getting the whole martensite. Now, how to change these hardenability. So, basically with the use of alloying elements you can very well change the hardenability, and you can have the conversion to martensite, full martensite structure. So, what we do is normally if you go for a alloy steel. So, effect of alloying element is there on these TTT diagrams. So, if you take the nickel chrome moly steel. So, if you this is a low alloy steel, and if you try to see the TTT diagram for such steels, what you see that there will be shift in the these the curve, and the shift is towards the left. So, if there is shift towards the left, so if suppose this line itself shifts towards left, so you have more freedom. So, you can have for any cooling rate you will have more chances of having the transformation to martensite. So, what happens that for such so if your this line is A1 and this line is A3. Now, in this case your and this is your MS and MF temperatures. So, if suppose this is your MS and MF temperature, in that case if you try to see the curve goes like this way. So, this way it goes. So, what you see that and this is your Benetic zone, and towards this side you will have alpha plus perlite, you will have another zone which will be coming here, and this will be alpha plus gamma plus perlite, and you will have gamma plus alpha. So, that way what you see that because of the use of alloying elements, now this is your time, and here your if you see this will be 10 seconds, and this will be 10 raised to the power 2 seconds, this will be 10 raised to the power 3 seconds, like that. So, what you see in normal case your nose was close to 1 second, whereas in this case it is even after this about 10 seconds of time. So, there is shift of the nose towards the right, and that basically increases the hardenability, and in normal case also you can have the formation of martensite with the addition of alloying elements, and that way it will be affecting these TTT diagrams. So, this is in nutshell about the TTT diagram, and we have seen that how these diagrams can be read, how by referring to these diagrams you can understand that with certain cooling rate or at what temperature and with what time what amount of transformation will be there. So, what will be the different phases which you are likely to get. So basically this kind of transformation where you are coming and holding at this temperature and going isothermal transformation here coming. So, that gives you the magnetic transformation, magnetic phase. So, that way then you are coming into the martensitic zone. So, that is about this TTT diagram, and we will further read about the continuous cooling transformation diagrams. So, that is about this lecture. Thank you very much.